this programming assignment, which focuses on scheduling algorithms used by operating system to schedule CPU for different processes. This is a simulation to check the performance of different scheduling algorithm, first come, first serve, shortest job first, shortest remaining time, and priority scheduling with round robin as a tiebreaker. So the main part of the simulation, the main function, basically is defining simulate.c. I will share all these files that I'm going to show you today. So you can use them if you want and continue from where I stop at the end of this meeting. These are the functions that are defined in the simulate.c. I'm going to start with main2, which is basically the beginning of one round of simulation. In this function, which is going to be like the main function for one simulation, we are getting a bunch of parameters like n, which is the number of processes that we want to simulate, k, the arrival interval. So if k is 100, that means we are evaluating, or we are studying the system from time, assuming that the processes arrive from time 0 to 100. D is the average CPU time, or the mean CPU time, which is basically the average amount of the average of CPU times, the average of CPU burst times, I should say. And STD and V is the standard deviation of the CPU burst time. So the assumption is the CPU burst times are following a normal distribution, a bell-shaped curve, with the average equal to D and standard deviation equal to V. And then Q is the value of time quantum for the last algorithm that we want to simulate, which is the priority with round robin. The time quantum is a value that the round robin algorithm uses to find out when the timer times out and the processes should leave the CPU and give the turn to the other processes. And then the rest of it is basically evaluating those arguments and initializing the processes. The processes will be initialized in this function, and this function basically goes through this for loop and sets the arrival times, remaining times, active or passive, turnaround time and priority value for each process, using some random number generators or some constant values. For example, the arrival times would be a uniformly distributed random number from 0 to k, or the total CPU time would be a normally distributed random number with a standard deviation of V and average of D. And then, the priority level would be a random number from 1 to 10. And that would be used for priority scheduling. Yeah, that's pretty much it. And the active would be either 0 or 1. Those who arrive at time 0 would be active. Everything else would be inactive. Yeah, that's pretty much how to initial. That shows you how to initialize all the processes with random numbers. And then it simulates the first come, first serve. Then it simulates the shortest job first. Then it simulates the shortest remaining time. Then it simulates the priority scheduling with round robin. Between each simulation, for example, between first come, first serve and shortest job first, it will do the following. It will do these two operations. The first operation is computing the average turnaround time so that you can measure how good or bad first come, first serve did by finding the average turnaround time of the algorithm. Turnaround time is the total time it takes for a process to be executed from the moment it gets into the system until the moment that it gets terminated, because its burst time is done, or burst time is gone, or the remaining time is 0. The other operation is reset processes. The reset processes is basically the function that resets everything to the initial values. So basically, it sets the remaining time back. It resets remaining time by setting it equal to the total CPU time. It makes all the processes active flags 0 except for the ones who arrive at time 0, and then it sets the turnaround time of all processes as 0. You may wonder what processes are. Processes are an area of max processes of process structure, which is defined in simulate, that's H, and you can see this here. It has all of these parameters, and it basically represents one single process. And max processes is set to 1000. If you look at the simulation numbers, I think 1000 is good enough. Before I start going through the details of the simulations, let me also review one more thing. This main2 is not the real main of my simulation. I have another main function, which is going to run the simulation for multiple scenarios. These are my 4 scenarios. These are the value of n and k. The first one says n is 100, k is 1000. The second one says n is 500, k is 10,000. The third one says n is 500, k is 5,000. And the last one says n is 1000, k is 10,000. And these are all specified in the assignment specification. We want to run this simulation 4 times. So we give it like 4 different set of values. And then, the very first one is the smallest one because we only need to run for 100 processes. The last one is the biggest one because we run it for like 1000 processes. And then the time intervals that processes arrive is different. The first one has 1000 seconds or 1000 units for the processes to arrive. The last one has 10,000 time units. So the processes will arrive in a longer period of time. There are 4 scenarios here. In each scenario, we give a different we give 25 different values to D, which is the average CPU burst times. The average CPU burst time change will vary from k over n to 25 times k over n. And this step is k over n, so it's gonna change 25 times. And that basically means we run the simulation 25 times for each scenario. There will be 25 execution per scenario. And you have 4 scenarios, that would be 100 runs of the simulation in total. And each simulation is made of 4 algorithms. So you will get 400 numbers, not 16 numbers. I have to take it back. So the summary is this. You have 100 runs. Each run will execute first come, first serve. The shortest job first. The shortest remaining time. And a priority with round robin. This one will give you one number, which is the ATT. This one gives you another ATT. This one will give you another ATT. This one will give you another ATT. So we have 100 runs. Each run will give you 4 numbers. So we have like 400 numbers. These 100 runs are basically across these 4 scenarios that I mentioned. In each scenario, N and K are constant, but the D value will change 25 times. So this is the big picture of everything that you need to run. But you don't need to touch this part. Just you have to take care of drawing the plots at the end, which I explained in the other video. In the other video, I explained how first come first serve is simulated. And if you go through that, it's very obvious how first come first serve works. Basically, you have to create a queue, which you have done it for assignment 1. And then the process, we call this the ready queue. The processes will arrive and get into that ready queue. And when they finish, they will get out. And it's that simple. When a process arrives, you let it run and you give the CPU to that process. And you don't interrupt that process in any way, shape, or form. Let it finish. When it finishes, then you get it out, right? And that's it. It's like super simple. All you need to do is to use queue. And I have created my own queue. I explained that in the other video, so I pretty much don't want to go over the details of it, but this is how the queue.h looks like. You have a queue that is implemented using a linked list. The node of a linked list looks like this. It's a single linked list. And you have the init queue for initializing the queue, enqueue, dequeue for adding or removing from the queue, and peek, which is going to look at the top of the queue, and toStr, which is going to print the queue. That's only for debugging purposes. When you want to see if your algorithm works or not, then you want to print it out, and toStr works. toStr helps you to print that queue, the content of the queue, so you understand how it looks like. And Q.C implements every single one of these functions, as you see. Even the toString method is implemented here. And then the first come first serve uses it. Whenever a process arrives, it calls the enqueue function. Whenever the process finishes, it calls the dequeue function. The queue ready is initialized using the init queue, and everything else is straightforward. You don't even need to be worried about this. This is a very simple algorithm, but you can take advantage of this and use it to create the last algorithm, the priority queue with round robin, because in priority queue with round robin, you need 10 ready queues. So this is going to be a very good starter code for the last algorithm, which is priority queue with round robin, because in the last algorithm, you need to have 10 of these ready queues, 1 ready queue for each priority level. And the way that algorithm works is that while the more important processes which go into the top queue is not empty, you don't look down to other queues. So you always have to take care of the highest priority queue or highest priority line or queue. And then you need to look at the second highest one, third highest one, all the way to the lowest priority queue. And then run the processes in that order. In each queue, we have a round robin algorithm. Round robin basically means every process will run for a few seconds. We call that the time quantum. When they are done, they have to go back and they will be inserted back to the same queue. And then this process may happen multiple times. So let's say you have 4 processes in this queue, 1, 2, 3, 4. Each of them will be executed for Q seconds. Q is the time quantum. And then they will be thrown out of this queue, and then they will come back to the end of the queue. So first we run 1 for a few seconds, then we run 2, then we run 3, then we run 4. And then every time that they finish, they will be dequeued from the queue and they will be in-queued into the same queue. When one queue is emptied, then you go to the next level queue. There are 10 of them. So the reason we call this priority scheduling is because there are 10 different ready queues. Therefore, you need to have something like this. You need to have 10 ready queues, and then you need to have this for loop to initialize all the queues. I just showed you very basic changes that you need to make to create the other algorithm, but I haven't done anything else. You have to take care of all the other details for this algorithm. Let's clear everything. Let's move forward to shortest job first. Today I'm going to show you the shortest job first as well, and then I leave the other two algorithms for you. So in the previous video, I explained first come first serve. In this video, I'm going to focus on shortest job first. And you may say, well, you spent, I don't know how long, you spent like 20 minutes explaining all of that. But I just wanted to make sure you understand everything before that. I'm going to quickly go over shortest job first and the way it can be done so that you can run or you can create the shortest remaining time yourself. So in this video, I'm going to show you how shortest job first works. And I'm going to explain that using the data structure that you have created in assignment 1, which is called binary heap, which is a priority queue algorithm. It's a priority queue data structure. And after I'm done with this explanation, then you can change this algorithm a little bit so that you can create the shortest remaining time. Shortest remaining time algorithm and shortest job first algorithm are basically the same algorithms with one key difference. Shortest job first is non-preemptive. Shortest remaining time is preemptive. What's the difference between non-preemptive and preemptive? In a non-preemptive scheduling algorithm, a process cannot, the CPU cannot be taken away from a process forcefully. So when a process acquires the CPU, it can use it as much as it wants. When it finishes, then it's gonna leave the CPU. But in a preemptive setting, the CPU can be taken away from a process forcefully without the, like, not voluntarily. So basically, a process needs 10 seconds of CPU. After 2 seconds, we can say, okay, this process needs to be removed from CPU. The CPU has to be given to a different process. That's called preemption. So shortest job first is non-preemptive, but shortest remaining time is preemptive. That's the difference. I'm going to show you the shortest job first, and then you do the non-preemptive version, which I believe it's easier. I'm sorry, you do the preemptive version. So this is the non-preemptive, which I believe is harder. I'll show you that. And then you do the preemptive version, which is called shortest remaining time. In order to do the shortest job first, the most efficient way is to use a priority queue, which is a binary heap. So I have used pq.h, which stands for priority queue.h, and it basically implements a binary heap. The priority queue.h basically defines this structure, which is called priority queue, or we call it binary heap in data structures. It gets a list of processes. It's an array of processes. The size and the capacity. Size means how many you have, how many processes you have right now inside that heap, which is initialized to 0. And capacity is basically the capacity of this array. You may say, well, this is not an array, it's a pointer, but in C, arrays can be cast to pointers easily. We have an init PQ which is going to initialize this priority queue. We have an in queue for shortest remaining time. We have an in queue for shortest job first. We have a D queue for shortest job first and shortest remaining time. So you may say, wait a minute, why do you have like two different in queue and D queues, one for shortest job first, one for shortest remaining time? The reason is in shortest job first, the key or the value that we look for in a process is total CPU time. But for shortest remaining time, the key of the heap, the value that you're looking for heapify, for percolating up and down or heapify operation, is not total CPU time. Instead, it is the remaining time. So let me go back to simulate.c. I'm sorry, simulate.h to tell you which ones we are talking about. So the total CPU time is the key for shortest job first priority queue. The remaining time is the key for shortest remaining time priority queue. So that's the difference. Because in a shortest job first, you care about the total CPU time. But in the shortest remaining time, as you can imagine by the name of it, the thing that the quantity that you care about is not the total CPU time. Instead, it's the remaining time. So that's why we do have two different versions of in-queue and D-queue in our priority queue. So that's the reason. And then you have a peak operation, which is, if you remember from your data structures class, the peak basically grabs the root of the binary heap, which is the first element in the array. And that's pretty much what it does, and it doesn't depend on, shortest remaining time or job first. It only looks at the first element in the array. So we only have one version of the peak, and then freeing is going to deallocate the memory that is given to the list of processes, and then this is PQ to a string, which is going to convert a priority queue to a string so that you can print out the contents of every priority queue at any moment you want, so that if you want to debug your code, you can do it. So with that explanation, let's get into, I'm not going to show you the details of this. I'll share it with you. You can look at it yourself. Probably if you have already done the assignment 1 successfully, you have your own code for a binary heap, but this is just how to initialize a priority queue for in queue and DQ. We have operations called heapify up and down. We have two in queues, one for SRT, one for SJF, which is gonna call the heapify up or percolate up. The DQ operations will call heapify down. And then we have like two different versions of DQ and two different versions of InQ. They work. You don't need to be worried about whether or not they're correct. I'll share these with you. Let's continue the simulations job first. So after you initialize the priority queue, you set the CPU status to free. CPU status is a flag that is either free or busy. What does CPU status mean? If there is no process actively being executed by CPU, the CPU is free. It's not busy. Right? If the CPU is running a process right now, we call that busy. Why should we keep track of the CPU status, see if it's free or busy? Because we are dealing with a non-preemptive scheduling algorithm called shortest job first. So if the CPU is busy, we should not accept any new process by the CPU. The CPU is busy, so it cannot switch between processes. The CPU should keep running the same process that is running right now. That's why we have this flag. But for shortest remaining time, you don't need to be worried about the CPU status. That's why I told you earlier that shortest job first is harder to implement than shortest remaining time, because in shortest remaining time, you don't really care whether this is whether the CPU is busy or it's not busy. You can preempt a process and replace it with another process if you want. You can just prevent the process from running and give the CPU to another process. Anyway, so for this algorithm, the CPU status matters. So we set it to free first. Then we say in this while loop, as long as you haven't finished all the processes, completed is the number of completed processes. As long as this is less than n, we are going to do this for loop. This for loop basically checks whether we have a new arrived process. It says if the process arrival time is equal to t for any of the n processes, and t is the current time, then set them to active and add them to the shortest job first priority queue. And you just add them to the priority queue, right? So this is gonna take care of the arrivals. Who is going to arrive at time t, which is the current time. If the ready queue is empty and the CPU status is free, that means nothing's going on right now, then increase the time and continue. And this is gonna just do nothing. It's gonna say, okay, nothing's going on, no processes arrived, and the CPU is doing nothing, so let's fast forward. Let's add the time of simulation by 1 and see what's going on next. Otherwise, if the ready queue is not empty or the CPU is busy, check whether the CPU status is free or not. If it is free, that means the CPU has just finished the process, so it is now accepting new process. So DQ one process from the heap, the one on the top, basically you're DQing the root of the binary heap, the one with the shortest total CPU time, and set the CPU status to busy. That means the CPU just started working on a new process. When you do that, then reduce the remaining time by 1 because the CPU is going to work on this current process for 1 second. So the remaining time will be decreased by 1, and then increase the simulation time by 1, and then check whether or not this process is going to be terminated right now. Because you're reducing the remaining time, there's a chance that the remaining time reaches to 0. If it reaches to 0, that means the process has just finished, it's just terminated. If that happens, the process is not active anymore, and you can now start calculating the turnaround time because you know the finish time, which is the current time. You know the arrival time, that's already stored in the structure corresponding to that current process. So subtract the arrival time from the finish time, and that's going to give you the turnaround time. The completed is going to be added by 1 because you just finished one more process, and then the status of the CPU is now set to free because the CPU had just finished one process, so it's not working on any process actively anymore. And you do this while loop as long as all processes finish. When they all finish, then they all have their own turnaround time, and then you can calculate the average turnaround time. And just to tell you where the average turnaround time is calculated, it should be in this function. Turnaround time total is set to 0. You just add all the turnaround times together, and then divide this by the number of processes to get the average turnaround time, and that's pretty much it. So that's how you calculate the average turnaround time at the end. So I just showed you the shortest job first. You can do the shortest remaining time in a similar fashion. So that's empty. It's for you to fill it up. but you need to use priority queue, obviously, because shortest remaining time is just like shortest job first. It always pick a process with the shortest remaining time. The shortest job first, look at the shortest total time, but shortest remaining time, look at the shortest remaining time, not the shortest total CPU time. And then this is empty too, because this is very similar to first come first serve. So I have shown you the first come first serve in the previous video, shortest job first in this video. The expectation is that you complete the other two. Shortest remaining time is similar to shortest job first, and priority queue is similar to first come first serve. All right. Thank you, everyone. Any questions? All right. Have a great day. Bye.